Häagen Dazs, Ben & Jerry's, and Tillamook make some of the richest ice creams on earth. Behind every pint lies a blend of pure cream, fresh ingredients, and high-speed freezing that locks in signature texture and flavor. Today, we go inside the creameries to see how these iconic brands churn, swirl, and freeze their way to perfection, one scoop at a time. Häagen Dazs ice cream isn't just made, it's crafted in a factory that operates more like a precision lab than a frozen dessert plant. From the moment raw cream arrives at the facility, every step is monitored, measured, and fine-tuned to turn just 5 base ingredients, cream, milk, sugar, eggs, and flavoring, into the kind of ice cream that scoops like velvet and melts like butter on the tongue. Behind the luxurious mouthfeel and slow melting density is a process that's deceptively complex. The Häagen Dazs production line doesn't move at the speed of most factory-made ice cream. It's slower, colder, and stricter, built for richness and texture, not just volume. And it all starts with sourcing ingredients at a standard far above most industrial suppliers. The factory receives fresh cream and whole milk daily. These arrive in insulated stainless steel tankers and are pumped directly into refrigerated silos. Unlike many ice cream brands that use ultra-filtered or reconstituted dairy, Häagen Dazs uses high butterfat cream, typically around 36–40%, compared to standard milk fat levels of 10–14%. That's a big reason why Häagen Dazs feels heavier, smoother, and more indulgent. The fat content plays a key role in flavor release and texture. Inside the ingredient preparation room, the cream and milk are blended with liquid sugar, a pre-dissolved syrup that integrates better and eliminates graininess. To this, egg yolks are added, not powdered or imitation emulsifiers, but actual yolk, which acts as a natural stabilizer and gives the ice cream a custard-like body. For most varieties, that's it. The base is just cream, milk, sugar, and egg yolk. Simple, but precisely balanced. Next comes pasteurization, which doesn't just ensure safety, it also sets the stage for texture. The mixture is pumped into a plate heat exchanger, where it's heated to around 180 degrees Fahrenheit for about 30 seconds, then rapidly cooled to just above freezing. This kills bacteria, but also alters the protein structures in the milk, giving the ice cream base better structure and scoopability later on. Once pasteurized, the mixture flows into aging tanks, enormous stainless steel vessels where the liquid base rests for 12 to 24 hours at near freezing temperatures. This aging process is crucial. It allows fat globules to crystallize slightly and proteins to fully hydrate. Without this resting period, the texture would be thin and icy. With it, the base becomes thick, rich, and ready to carry flavor. From there, the base is split into multiple flavor streams. The factory is divided into lanes, each designed to handle different inclusions and flavor profiles. For vanilla, real vanilla extract is added directly into the base. For chocolate, melted chocolate or cocoa paste is blended in. Fruit flavors use purees that have been filtered and flash pasteurized off-site to preserve color and aroma. Everything is batch dosed by weight and logged digitally. No guesswork, no approximation. Then comes homogenization, a high-pressure system that forces the mix through narrow valves at thousands of psi. This breaks down the fat globules into microscopic particles, distributing them evenly throughout the mixture. Homogenization gives the ice cream a uniform creaminess and prevents fat separation during freezing. It also ensures that every bite tastes and feels the same, with no greasy streaks or watery gaps. Once flavor is blended and homogenization complete, the liquid ice cream is pumped into freezing barrels, where the real transformation begins. These barrels are jacketed with refrigerant coils and filled with rotating scraper blades. As the liquid base flows in, it's cooled to about 20 degrees Fahrenheit, while the blades continuously scrape the forming ice crystals off the inner wall, ensuring a fine, smooth texture. Air is injected into the mix at a controlled rate, a step known as overrun. Here's where Häagen Dazs breaks from the rest of the industry. Most ice creams are aerated by up to 100%, meaning half the volume is air. Häagen Dazs allows no more than 20-25% overrun, resulting in a denser, heavier product. That's why pint feels so solid in your hand. Less air means more actual ice cream per bite and a slower melt in the bowl. The semi-frozen ice cream, now the consistency of soft serve, is funneled into filling machines. For pints, it's portioned by volumetric fillers that deliver precise amounts into each container. Every container is pre-chilled to prevent melting on contact. The flow must be perfect, not too fast, or air pockets will form. Not too slow, or the ice cream may start to freeze mid-transfer and block the nozzles. For flavors with mix-ins, chunks of chocolate, caramel swirls, nuts, or cookie dough, the inclusions are added at the very last second. Dedicated feeder systems deposit inclusions into the flow just before it enters the pint, using augers and vibration tables to ensure even distribution. The timing has to be razor precise. Add-ins must suspend evenly in the dense ice cream without sinking to the bottom or clumping at the top. After filling, each pint is lidded, sealed, and sent into a blast freezer, where the temperature drops below 40 degrees Fahrenheit. This rapid hardening phase locks the microstructure of the ice cream in place, preventing the formation of large ice crystals. It's one of the most critical steps. Without hardening, the fine structure created in the freezing barrel would collapse, leaving behind a grainy texture. Inside the blast freezer, pints ride through a spiraling conveyor for several hours. The air is dry and super chilled, moving across the containers in high-speed bursts. The goal is to bring the core of each pint to storage temperature, around 20 degrees Fahrenheit, as quickly and evenly as possible. Any delay here, and the product risks texture degradation. From the blast freezer, pints move to a labeling and boxing line. Each container is sleeved with its printed label, stamped with a production date and batch code, and scanned for weight consistency. Quality control technicians pull samples constantly to test for fill height, texture, flavor, fat content, and microbial stability. The ice cream is even tested for its melt curve, how fast it softens at room temperature, since melt resistance is part of the brand's identity. Finished pints are packed into insulated boxes and sent to deep frozen storage, massive cold rooms kept at 20 degrees Fahrenheit, with double-door airlocks and constant monitoring. Inside, pallets of Häagen Dazs are stacked sky-high, awaiting distribution. The logistics are timed with weather, route temperature averages, and transport times to ensure the ice cream arrives frozen solid and uncompromised. Even the trucks are pre-cooled before loading to prevent thermal shock. Sanitation inside the factory is relentless. Every stainless steel surface is hosed down, steamed, and chemically sterilized daily. The filling nozzles, augers, pumps, and hoppers are all dismantled between flavor runs and scrubbed in industrial wash stations. No cross-contamination, no lingering allergens. Every flavor change means a full line flush. Air inside the plant is filtered and pressurized. Employees wear full-body suits, gloves, masks, and hairnets. Entry to the production floor requires passing through an air shower. Even the water used for cleaning and cooling is filtered multiple times to remove minerals that could affect the equipment or final product. Data flows through the entire system in real time. Temperature probes, viscosity meters, pressure sensors, flow trackers. Every phase of production is logged and monitored through central dashboards. If something drifts even slightly out of spec, a dip in freezer temp, a pump moving too slowly, the line adjusts automatically or triggers an alert. And while many ice cream factories are built for speed, the Häagen Dazs plant is built for control. The lines move slower, batches are smaller, There's more holding time, more testing, more calibration. The entire system is engineered to produce richness, not just volume. Even the packaging is part of the process. The containers are triple layered and coated to resist freezer burn. The lids are pressure sealed to prevent air infiltration. Labels are designed to hold up in extreme cold without peeling or fading. And every element of the container, from its shape to its material, is chosen to preserve the internal temperature for as long as possible outside the freezer. So while a pint of Häagen Dazs might feel simple in your hand, just a clean container filled with ice cream, the process behind it is anything but. From liquid dairy to frozen scoop, every step is measured, chilled, sealed, and scrutinized. It's not just a factory, it's a climate-controlled ecosystem dedicated to one product. Ice cream that tastes indulgent, melts slowly, and leaves nothing to chance. Inside the Ben & Jerry's factory, ice cream isn't just made, it's celebrated. Chunky, swirly, creamy, and deliberately over the top, each pint that rolls off the line is the product of a factory system designed to never say no to a mix-in. While most ice cream plants are built for uniformity and efficiency, Ben & Jerry's production lines are built to embrace chaos. Massive brownie chunks, peanut butter cores, caramel ribbons, full cookie pieces, folded into frozen custard with wild precision. And it all starts with an unflavored, off-white liquid base held in chilled stainless steel tanks. The process begins in the mix room, where the core ingredients, cream, condensed skim milk, liquid sugar, egg yolks, and stabilizers, are blended together to form the unflavored ice cream base. This isn't your average low-fat mix. Ben & Jerry's uses a high butterfat blend, around 14-16%, which gives the final product its signature scoop resistance and creamy mouth-coating texture. The mix is pumped into 1,000-gallon jacketed tanks and agitated to ensure full emulsification before moving to pasteurization. Pasteurization is critical, not just for food safety, but for structure. The base is heated to 180 degrees Fahrenheit, then rapidly cooled to below 40 degrees Fahrenheit using a plate heat exchanger. This flash cooling locks in the emulsion and prepares the mix for aging, which takes place in aging vats for 4 to 8 hours. During this time, fat globules solidify slightly and proteins hydrate fully, creating a base that whips up smoother and holds air better in the freezer. From here, the mix is routed to flavor vats, where the base gets transformed into one of dozens of specific flavor recipes. Real ingredients are used: pure vanilla extract, fair trade cocoa, banana puree, fruit jams, and coffee concentrate. Each flavor is stored in sealed, cooled chambers with individual dispensing lines to avoid cross-contamination. Once added, the mix is homogenized again, ensuring flavors are fully incorporated. Then it's time for the freezers, and this is where things get loud and fast. The liquid mix is pumped into continuous freezers that operate at sub-zero temperatures, usually around 22 degrees Fahrenheit. Inside, rotating scraper blades freeze the mixture against the chilled walls while injecting a carefully measured amount of air, known as overrun. Ben & Jerry's uses low overrun, about 20-25%, making their ice cream far denser than most. It's one of the key reasons why a pint feels heavy, scoops slowly, and melts luxuriously. The result at this stage is soft serve consistency, thick but pliable. That's when the real Ben & Jerry's identity kicks in, the chunk feeder. Mounted directly onto the output of the freezer, the chunk feeder is a stainless steel auger system that folds in large, often unwieldy inclusions. This is where chocolate chunks, brownies, peanut butter cups, cookie dough balls, caramel swirls, marshmallow ribbons, pretzel bits, and pie crusts are fed into the mix. Not sprinkled, but dumped. The chunks are stored in cooled hoppers to prevent melting and are released at programmed intervals. Sensors monitor chunk size, density, and flow rate to ensure even distribution. Ben & Jerry's inclusion sizes often break the rules of conventional ice cream manufacturing. Whereas most brands aim for 1/4 inches particles or smaller, Ben & Jerry's regularly includes chunks over 1/2 inches in diameter. That means the entire system, from the chunk feeder to the pint filler, has to be engineered to let large solids pass without jamming. Conveyor belts are wider, augers are stronger, and the valves are oversized to accommodate anything from gooey brownies to whole nuts. Once the mix-ins are blended into the semi-frozen base, the ice cream flows directly into pint fillers. Automated machines that fill pre-chilled pints in a single downward plunge. These machines must fill quickly and cleanly without air pockets or uneven distribution. The fill level is carefully controlled so that chunky pieces don't rise above the lip of the container. Any overfilled or underfilled pints are kicked off the line automatically. After filling, the pints are lidded and flipped upside down. This upside down hardening technique helps create a smoother top surface as the soft ice cream settles against the lid, reducing air gaps and forming a clean freeze cap once solid. It's a detail rooted in old school ice cream wisdom, and Ben & Jerry's still does it by the book. Next, the pints are sent into a spiral hardening tunnel, a blast freezer where the internal temperature can reach 60 degrees Fahrenheit. This spiral system slowly rotates the pints upward on a winding belt, exposing them to high-velocity, frigid air. The goal is to freeze the entire pint uniformly and rapidly, typically within 90 minutes, to preserve the microcrystalline structure created during initial freezing. Fast hardening prevents large ice crystal growth, ensuring the final texture stays smooth even after weeks in transit or storage. Once hardened, pints are flipped right side up and sent to labeling lines. Labels are applied using high-speed sleeves that wrap the container and heat seal in place. Each pint is then date-coded, stamped with a batch number, and scanned for alignment, print quality, and lid fit. This is also where quality control techs perform random sampling, cutting pints in half to assess chunk distribution, freeze depth, swirl integration, and overall appearance. From here, the pints head to the pack-out area, where robotic arms load them into cartons or trays based on destination. Ben & Jerry's products are distributed globally, so packaging lines may vary depending on labeling language, country-specific ingredient regulations, or promotional campaigns. Boxes are sealed, barcoded, palletized, and moved into deep frozen storage, where they rest until transport. Even logistics are engineered for the product's texture. Trucks used to haul Ben & Jerry's are pre-cooled to 20 degrees Fahrenheit before loading. Pallets are organized so airflow can move between cases, keeping the product frozen evenly across long hauls. And the boxes themselves are insulated to resist sudden thermal spikes during dock transfers or warehouse rotations. Hygiene and food safety are taken seriously at every stage. The production floor is kept under positive air pressure to prevent contaminants from entering. Workers pass through gowning rooms and foot sanitizers before entry. Equipment is cleaned daily using a combination of steam, food-safe detergents, and high-pressure rinse systems. Flavor changeovers require full disassembly and sterilization of tanks, pipes, chunk feeders, and fillers, especially when allergens like nuts or dairy alternatives are in play. Digital control systems track every variable in real time: mix temperature, overrun percentage, inclusion density, pipe pressure, freezer performance, even label placement. If anything drifts outside of spec, alarms notify operators and can halt the line instantly. Data from every batch is logged and stored so that every pint can be traced back to the exact time, room, and ingredient lot it came from. And unlike most factories that prioritize speed above all else, Ben & Jerry's lines often run slower by design. Some flavors have so many mix-ins or swirl complexities that rushing the process would create distribution problems or mechanical jams. The factory is built to say yes to chunky creativity, even if that means modifying machines for one limited edition flavor that only runs for 2 weeks. There are even unique systems in place for core pints. Those with a column of peanut butter, caramel, or fudge running down the center. These require a dual nozzle filler with a center core injector. First, the base ice cream is deposited in a ring shape. Then the core is injected down the center, and more ice cream is added to seal the top. It's a slower, more intricate fill, but one the factory is equipped to do on demand. At full tilt, a Ben & Jerry's factory can produce hundreds of thousands of pints per day, each one a highly engineered blend of frozen custard and structural indulgence. But it's not just about volume, it's about holding true to the brand's philosophy. Every pint must be full of big chunks, real ingredients, and flavor combinations that are as wild on the inside as they are on the label. So, while a Ben & Jerry's pint might seem like dessert, it's also the end result of a factory built to break the rules of standard ice cream production, designed for gooey cores, oversized cookies, caramel rivers, and pieces so big they require custom-engineered feeders to stay on the line. Tillamook ice cream is made in a factory that feels more like a dairy cathedral than a frozen dessert plant. Rooted in Oregon's dairy country and backed by a century-old farmer-owned cooperative, the entire process is built around one idea: real ingredients handled with real care. Where other factories chase speed and scale, Tillamook's facility is engineered for flavor integrity, rich texture, and minimal processing, all while producing millions of pints per year with consistent, silky perfection. It all begins with fresh cream, sourced directly from the cooperative's own herds and partner farms in the Pacific Northwest. Every day, tankers filled with high butterfat cream and whole milk arrive at the factory's intake bay. The cream is cold, clean, and unstandardized, meaning it hasn't been stripped and reconstituted like it is at many large processors. It's pumped into refrigerated holding silos and tested immediately for fat content, temperature, and microbial safety. The first major step is blending the base. This happens in massive stainless steel mixed tanks where cream and milk are combined with liquid cane sugar, egg yolks, and stabilizers like guar gum or carob bean gum. Unlike many commercial ice creams that rely on artificial emulsifiers or corn-based sweeteners, Tillamook sticks to natural, clean label ingredients. The ratio of cream to milk is kept high, often resulting in a butterfat content of at least 15%, which is above the USDA minimum for premium ice cream. Once the ingredients are in the tank, the mix is agitated using large motorized paddles to ensure uniformity. At this point, the base is smooth and custard-like, pale yellow from the egg yolks. It's still completely unflavored, but this blend is what gives every Tillamook flavor its rich, dense mouthfeel, regardless of whether it becomes Marionberry pie or chocolate peanut butter. Next comes pasteurization, which is more than just a safety measure. It's about precision. The mix is pumped through a plate heat exchanger and heated to at least 180 degrees Fahrenheit for 25 seconds, then cooled rapidly to under 40 degrees Fahrenheit. This process kills bacteria and helps bind the fats and proteins in a way that sets the foundation for a creamy freeze. The pasteurized base is then moved to aging tanks, where it sits undisturbed at cold temperatures for up to 24 hours. This aging step allows the fats to crystallize and the proteins to fully hydrate, giving the base better stability during freezing. From here, the base heads to flavor dosing stations, small, enclosed bays where precise amounts of vanilla extract, cocoa, fruit purees, and other natural flavor compounds are blended into individual batches. Tillamook prides itself on using real ingredients: pure vanilla, actual chunks of Oregon-grown fruit, and hand-crushed chocolate. No artificial flavors, no chemical emulsions. Each ingredient is stored in chilled tanks or sealed hoppers and added through clean-in-place pipelines to prevent cross-contact and preserve freshness. For flavors that include mix-ins like fudge, caramel swirls, pie crust chunks, or peanut butter, Each add-in is handled in a dedicated solid system. These ingredients are kept chilled or frozen to maintain integrity and only added after the ice cream is semi-frozen to prevent melting, disintegration, or settling. The system uses augers, conveyors, and timed gates to fold in solids without crushing them, ensuring they're evenly distributed and maintain their shape and texture. Then comes the heart of the process, the continuous freezer. The flavored base is pumped into barrel-style freezers lined with ammonia-cooled jackets. Inside, rotating scraper blades spin against the frozen walls, preventing buildup and keeping the mixture in constant motion. As the base freezes to about 21 degrees Fahrenheit, air is injected into it to create volume. But unlike many brands, Tillamook uses very low overrun, usually around 20%, meaning the finished ice cream is only 20% air by volume. That's what gives it that dense, slow-melting texture. For comparison, some cheaper brands may use over 100% overrun, making half of the pint just air. The semi-frozen ice cream, now the texture of soft serve, flows into filling stations. Each pint or tub is pre-cooled to prevent melting on contact. Volumetric fillers pump the ice cream into each container with precise weight and volume calibration. Any overfilled or underfilled containers are instantly flagged by weight sensors and removed from the line. Swirls and variegates, like ribbons of fudge, caramel, or berry compote, are added in line through secondary injectors that pulse the thick sauces in just before the pint is sealed. These injectors are programmed to create real ribbons and streaks, not just a blended-in flavor. It's what gives Tillamook ice cream its recognizable marbling when you scoop through a pint of Oregon strawberry or sea salt and honeycomb toffee. After filling, each container is lidded and sealed within seconds. Tamper-evident seals are applied, and the containers are flipped upside down, a technique that helps ensure a level, flat freeze on the top surface. The flipped pints are sent directly into a spiral blast freezer where sub-zero air circulates at high speed, hardening the ice cream to its core. Inside, the temperature often reaches below 40 degrees Fahrenheit, and the hardening process takes about 2-3 hours, depending on container size and flavor density. The hardened ice cream is then flipped upright, passed through labeling stations, and coded with batch information and best by dates. Optical scanners verify that the right label matches the contents inside. From there, pints move through a final inspection station, where high-speed cameras scan for lid alignment, label quality, and any visible container damage. Units that fail inspection are diverted, unpacked, and the ice cream is returned to rework stations, melted down, filtered, and reintroduced into the mix tanks to reduce waste. Finished pints are organized by robot-guided arms into crates and pallets. Every unit is tracked by barcode through a real-time inventory system, which logs flavor, batch, production date, and destination. Pallets are stored in an on-site deep freeze warehouse, maintained at 20 degrees Fahrenheit, and separated by production date for organized first-in, first-out rotation. Even the transport logistics are designed with temperature precision. Refrigerated trucks are pre-cooled before loading, and shipping routes are optimized to minimize thaw risk. Temperature sensors embedded in pallets track ambient conditions during transport, and alerts are sent to logistics coordinators if temperatures drift beyond safe range. Cleanliness is built into every stage of the facility. All equipment, pumps, hoses, vats, mixers, chunk feeders, is cleaned between every flavor run using a clean-in-place (CIP) system that circulates high-temperature, food-grade cleaning solutions through closed-loop systems. This allows full sanitation without dismantling every pipe and tank manually. After each shift, the production area is deep cleaned and swabbed for microbial traces. Swirl injectors, pint fillers, and batch tanks are tested regularly for allergens, with documentation tied to each production run. Environmental controls also play a major role. The air inside the plant is HEPA filtered and humidity controlled to prevent condensation and airborne contaminants. Workers wear full protective gear and must pass through airlocks and hand wash stations to enter any food contact zone. Even the water used in pasteurization and CIP systems is filtered to remove minerals that could affect taste or equipment longevity. Each batch is sampled and tested by in-house sensory teams who check for texture, flavor accuracy, chunk distribution, swirl clarity, and scoopability. There are texture analysis machines that measure spoon pressure required to cut through a pint, along with melt rate tests and freeze-thaw cycling simulations to ensure the product performs consistently, even after multiple home freezer openings. Chooses only russet Burbank potatoes for their fries. These aren't your average spuds. They're chosen for their unique qualities, making them perfect for frying. These potatoes aren't picked just because they taste good. They're also chosen because they can keep the proper quality and texture even when made in big batches for fast food. Take the United States, for instance, where russet Burbank potatoes are a top pick, and most McDonald's contractors are from the US. Here, you can see how the potatoes are dug up from the ground with the help of heavy-duty, all-in-one machines. Inside these machines, advanced tools clean the potatoes, removing all the dirt. This process continues until all the potatoes are gathered. All these potatoes are then collected and stored in a room. This way, they can be quickly taken out when needed, ensuring that the processing never stops. You'd be amazed by the sheer quantity of potatoes here. Believe it or not a single potato goes bad. They're all used up within 15 days. A big reason for this is that McDonald's makes approximately 9 million pounds of French fries every day. As soon as these potatoes are taken to the factory as needed, that's when the real magic begins. Let's take you inside the factory, where you'll see French fries being made. First up, we've reached the potato washing station. Here, the potatoes are tossed into cleaning containers filled with water. Thanks to vibrating belts, the fast-flowing water easily washes away the dirt from the potatoes. After a thorough wash, a portion control elevator lifts the potatoes out of the water and transfers them to another belt. This belt gradually collects the potatoes in a container-like hose, sending small batches to the peeling machines for further washing. The peeling process is incredibly delicate, ensuring only the skin is removed without wasting any part of the potato. Once the potatoes are peeled and clean, they're moved through belts to the third washing chamber. Here, the final wash takes place with water containing chlorine and safe chemicals. Freshly washed and ready, these potatoes are then taken by the belts for special treatments. What you're seeing, all these units standing tall, are actually fine cutting chambers. They expertly cut the peeled potatoes into uniform sizes. This is why McDonald's fries always look the same in shape and length. Their machines work in a precise and effective way. The machines propel the potatoes at speeds of 60 to 70 mph through high-pressure water knives. These water knives finely slice the potatoes into thin strips, which are then sorted by their size and shape. After being cut, the fries are washed again and then placed on an automatic elevator, taking them toward the boiler for the next step in their journey to becoming perfect fries. Sometimes the cut fries get special treatment with a mix of sugar and sodium acid pyrophosphate for two main reasons. The sugar helps the fries achieve that perfect golden brown color when fried, while the sodium acid pyrophosphate keeps the fries from turning grey or brown, whether they're cooked or frozen. The real reason they're boiled for a bit is to make the inside of the fries soft, so when they're fried later, they turn out crispy on the outside, but remain soft inside. The fries head straight to the boiler. Here, any broken or misshapen fries stick to the belts, while the perfectly shaped fries fall through to the boiling area. They're fried to 50% to lock in the quality, flavor, and freshness from the inside out. This step also removes some water and starch from the fries, creating a light crust on them. The oil they're fried in is a mix of canola, corn, soybean, and hydrogenated soybean oils. This blend is healthy because it doesn't contain trans fats or cholesterol. After the fries are half fried, they're taken out with an elevator and set aside to air dry. This usually takes about 5 to 10 minutes. During this time, any extra oil dries up, making the crispy, half-cooked fries ready for packing. The fries that are only half-cooked get frozen super fast in a special freezer tunnel. This keeps their taste and texture just right. Freezing them quickly is important to make sure they all look the same and can be stored without going bad. Potatoes can spoil quickly once they're peeled or cooked. After that, the fries are put in cool trucks or storage areas, all set to be sent off to restaurants. Cutting onions seems like the toughest part of cooking, right? It's the reason half of us are scared to even start cooking. But what if we told you that you could skip that mountainous task entirely? These machines are so efficient that no matter how you place the onion, they'll figure it out, set it right, and then, with the help of a belt that looks like a bunch of molds, make peeling and cutting super easy. First, gadgets that remove the tough outer layer grab onto the onion and peel it away in no time. Look at how cleanly and perfectly peeled these onions are now, all thanks to these fantastic machines. After a manual quality check to ensure no bad onions slip through, they're sent to be cut. This manual check is crucial. If there's a bad one, it can be caught and removed by hand. With incredibly precise cutting, all these onions are then packed and frozen, ready to help you out in the kitchen. If you want to get the job done without even touching the fish, don't worry, these machines will do everything for you. You won't have to touch them at all. These preset units seal a specific amount of fish into packets perfectly. It's rare for these machines to make mistakes. Well, to say they never do would be stretching it. They do make errors, but only at a rate of 0.001%, because they're tested over 100 times before being used in factories. First off, thanks to their excellent eyesight, these machines quickly sort out the bad apples to one side while the good apples gently move along the belt. These good apples are on their way to be turned into apple puree, which is used in a variety of delicious dishes. These machines process a ton of apples into smooth, sweet puree in no time. It's amazing to see apples zip through this process and come out as something that makes our food taste so good. The apple skins are removed and sent to another area, often ending up mixed into fodder at dairy farms. Here we have one of the biggest and most famous automated lines for making pancakes. You'll see everything from the batter being poured to the pancakes being cooked and layered, all done by machines without a hitch. These molds take a ride through an oven, where the pancakes are cooked until they're just right. Golden and delicious. After cooking, the pancakes are carefully picked up and arranged into neat stacks, ready to be packed and shipped out. Firstly, that beast machine steps into the fields and starts shaking, loosening the peanuts from the roots and turning them inside out. After the plants are dug up, they're left to dry in the sun for a few days. Now the excess moisture is removed from the peanuts, and they are ready to be picked up. Here come those bulky mechanical friends to do this job. Way much easier than it seems. It picks up the dried plants, separates the peanuts from other debris, and collects them in a hopper. From the last decade, China has been the largest producer of peanuts, and this strategic country usually makes a final count of around 20 million tons of peanuts every year. We have arrived at the facility where the entire peanut pile is fed into the cleaning setup. The unwanted stuff, like stones, twigs, and other foreign materials, is removed through pre-screening. This deshelling process is most satisfying when the machines delicately remove the outer shells of peanuts and reveal that beautiful, potential, and healthy nut we all were waiting for. Hang in there for a moment. They need to inspect manually for a quality check before they send the peanuts towards seed coating removing machines. Here, with gentle shaking, a lot of air pressure, and proper programming, that brownish skin is removed from the peanuts. The peanuts are treated with a medium boiling process to lock their texture and flavor and sanitize them by killing off any harmful bacteria or microorganisms by keeping the approximate boiling temperature near 121 stacking Celsius. However, it varies from company to company. As soon as the hopper is filled with the boiled peanuts, they are immediately packed and sealed in cans for distribution. These roasted peanuts are going to transform into something super buttery and delicious. Following a little roasting, the peanuts are cooled down to reach a temperature that is safe for handling and prevents them from becoming too hot or soggy during grinding. Those chosen peanuts take a trip towards this grinder and start revealing the smooth, buttery paste we all crave. It keeps grinding the peanuts until it reaches the desired smoothness, and the magic ingredients that will enhance the flavor keep being added little by little. This whirlwind of crushing and blending turns those nuts into pure deliciousness until it's homogenization. This step is chaos that gives way to harmony. Through higher pressure, the peanut butter gains its final and smooth texture. Witness this final stage where the bottles are getting filled and sealed to secure the fresh peanut butter inside. Automated machines, like filling and cap sealing machines, work tirelessly, ensuring each jar is brimming with creamy goodness. Each jar gets dressed up, ready to impress on the supermarket shelf. Whether spread on toast, topped over ice cream, or simply enjoyed with a spoonful, chocolate peanut butter never fails to delight the senses. Chocolate peanut butter serves the taste buds with its rich, creamy texture and harmonious blend of sweet and nutty flavors. Look at those different patterns those machines are creating to give us that satisfying sight. It's more like a powerhouse of protein and other essentials for muscle repair and growth. It's delicious and satisfies your hunger between meals. Those roasted peanuts are ready for a delicious chocolate coating. This chocolate coating process requires precision to ensure each peanut is evenly coated. After coating, the peanuts are left to cool and harden. Once cooled, they are carefully packaged into food-grade safe containers for distribution and sale. Have you ever tried these? Honestly, I never have. If we talk about those chilled, delightful ice creams, you all know it's pretty popular around the globe. Every day in the United States, people consume around 50 million ice cream pints. That's enough to fill more than 9 Olympic-sized swimming pools. Whether it's a hot summer day or a chilly winter evening, Americans' love for this sweet treat stays strong all year round. And why wouldn't it? Just look at how creamy, rich, and delightful they are. Have you ever tried these Taiwanese crackers? They are pretty familiar and loved by many, from adults to children. In addition to their delicious taste and texture, Taiwanese crackers are also celebrated for their simplicity. Made from basic ingredients, they create a magical burst of flavors inside your mouth. Their straightforward approach allows the natural flavors to shine through, resulting in an authentic and satisfying snacking experience. These snacks come in a range of textures, from crispy and airy to dense and crunchy. In the last few years, there have been several conspiracies about their oil spraying, but I don't think it is a problem. Because if you dig deeper, snacking as a whole would be considered unhealthy. But after much time, a little snacking won't hurt. Do you agree? No doubt at least their production is pretty satisfying to watch. Check out the magical power of these automated systems for juice-filling sectors, where every drop counts, reducing electricity consumption. You will barely see more than a few workers working around because of the efficient automation. Talking about these bulky productions is my love language. I always fall for them. Do you? If it's a yes, we are the same, bro. So cheers to that. I want you to comment down below and let us all know whether you prefer bottled or fresh juices and why that is. Think you had a hard time scooping out the sweet and juicy flesh from the pineapple shell? I ruined 4 large pineapples just to bring out a nice pineapple ring. Didn't waste the rest though. Surprisingly, burger meat patties are low in carbs. A beef patty typically has none unless extras are added. These delicious burger patties are full of energy and nutrients, perfect for fueling your day in the most appealing ways you have ever imagined. Dried apricots are far healthier, sweet-dried fruits that can be enjoyed on their own as a satisfying snack or added to various dishes like salads, oatmeal, trail mix, or baked goods for a natural. If we need to make that yummiest jam, we probably should focus on the healthy growth of the fruits too. Now this matter is being set under a strict guide. But yeah, giving those pots the healthier and fluffy mud with the precise amount of materials. Now these robots start at the bottom by planting strawberry plants in containers or pouches. Water is essential, so they water each pot carefully to keep the strawberries happy and hydrated. When the strawberries grow big and red, it's time to pick them. For this purpose, this gigantic robot activates its clutches to delicately pick the ripened strawberries only. Since they're on different levels, it's easy to reach and pluck the delicious berries. This entire automation is so beautiful and satisfying. How these robots peculiarly pick up the strawberry from the stem and cut it without harming it. In botanical terms, berries have their seeds inside the flesh, but strawberry seeds are on the outside, so they didn't consider it in the berry list. Those fresh strawberries have arrived at their final destination, and here they will get even royal treatment. Just a little stop for a weight check. Once they make sure the demanded number of strawberries has arrived, they take them to the sorting units. And you better know what's going to be here with them. Of course, keeping you in mind, they're going to take that stack of strawberries for a manual check and make sure that only good quality strawberries are going further. Once they're sure of that, they let them pass on until they reach safe hands. Yep, these people are going to place each strawberry in that mold for the game-changing results. These robots automatically detect the green hull of a strawberry and beautifully just remove it without harming any other inch of the fruit. This is mind-blowing. Everything is under mechanical control. You can see how sharp eyes they have. Come on, they're doing this for you. Strawberries grow close to the ground, making them more susceptible to dirt, sand, and even tiny insects. The first wash, often a combination of water and little vibrations, removes these surface impurities. That's very important. But you know, fruits and veggies like these need another bath too. That's why they're given a second wash, often involving specialized sprays or misting with solutions like chlorine dioxide, which takes care of the tougher particles like pesticide residues and bacteria. This double trouble approach ensures the strawberries are as clean and safe as possible. They care about you. We care about you. See how honored we are to have you, just like these red, juicy strawberries. These fresh strawberries are now put into these containers. Yep, that's how you get the true and fresh flavor of frozen strawberries, because they are the same as, what to say, straight from farms to your plate. They are packed and firmly sealed to lock the pulpy fruit inside the food-grade containers. Just check out that large number of cans. Secondly, they use some of the frozen strawberries to make that glittery, yummy strawberry jam. All these frozen berries are put into the carriers to take them to the next stop, which is to load them into a container to add further ingredients. As the strawberries are loaded, now it's time to add further ingredients like sugar. They make sure the jam looks good, tastes good, and has the perfect texture. Once the handsome amount of sugar is poured, they need to control those figures and machine's capabilities by playing with some important buttons. The hot water tub is ready for these beautiful entities to enter and get bathed in the sweet syrup. What are they peeking at? Okay, the real drama has just begun. Once all the pulp comes to mix in that syrup, they put that material through sieves. This is important to give you that pulpless, smooth, jiggly jelly jam. Mixing, and more mixing. Everything is heated up in big pots or machines to make the strawberries blend and taste awesome. A special thing called pectin is added to make the jam just the right thickness. It's time to cook the material until it reaches its perfect texture, and that desired texture can be seen here. I think it's done. Yep, he's going to test the jam base to see if it's ready or needs to be cooked more. And yeah, it's good to go. Now the final process begins, to churn the mixture, to add a little more smoothness and to cool it side by side. A little now, it's like letting the flavors and texture settle and become best friends before they get packed into jars. And just wait. Here we go. The whole warm jam base is ready. More close up here. It is, that creamy, smooth flow of my favorite jam. It's driving me crazy. Okay, time to pour that base and lock it in the jars. For that, these empty and starving bottles arrive. They are first neatly organized properly. The jam is carefully poured into jars all by itself. This process is usually automated in factories, with machines making sure each jar gets the right amount of fruity goodness. Here, we reach their sealing stage, where lots of lids are first picked in a proper style, beautifully conveyed to the roller coaster sort of belt, and finally to the sealing section where machines tightly seal the jars with lids. Okay, all those bottles are washed after being tightly sealed so that whatever sweetness remains on the outer side of the jars will be bathed away. We're now in the sticker section, where the robots will conveniently wrap stickers around these bottles so you will easily identify it's factory sealed. And of course, read that chart before eating anything. It's a good habit though. If you do, well, I don't. There's another technique too to add the labels one by one. All the bottles are labeled from whatever company they belong to and then piled up in the containers for the final bulk packaging. Bye-bye jam bottles. Don't forget my address and reach me soon. These mini jam bottles are filled up with the same freshness of fruit pulp and flavor to enrich your taste buds are those little nasty jam packets. You know, the ones at restaurants, tucked next to the bread basket, bursting with fruity sunshine in one tiny bite. They're more than just sugar bombs. They might be tiny, but they're full of flavors to serve as starters for every meal. Also, these bite-sized marbles help stop food waste and make sure every spoonful is just right. These machines are the backbone of many industries, from food production to textile manufacturing to construction. With their robust blades and precise cutting mechanisms, they're built to tackle even the toughest materials. Imagine a scene where smoky aromas fill the air as meat sizzles on the grill, tantalizing taste buds with every flip and sear. Curious about the staggering output of flatbread producing machines in a single day? Prepare to be amazed. These efficient marvels can churn out an impressive number of flatbreads thanks to their high-speed capabilities and precision engineering. Depending on the size and capacity of the machine, production numbers can vary widely, ranging from thousands to even tens of thousands of flatbreads per day. Crafted with the finest ingredients and expert techniques, our pastries are a symphony of flavors and textures. Meet chocolate depositors, the sweet secret behind every delectable treat. Hazelnuts are packed with nutrients like protein, healthy fats, fiber, and various vitamins and minerals. Not only do they promote heart health and aid in weight management, but they also support brain function and contribute to healthy skin and hair. These little blue gems are packed with antioxidants, which help fight off harmful molecules in our bodies and keep us feeling great. Motivate us to create more satisfying videos like these and smash the like button. These factories aren't just about quantity, they're about crafting quality too, ensuring that each slice of salami delivers a burst of savory perfection. Removing the skin helps trim down on excess fat and calories. You see, much of the fat in chicken resides in the skin. So by peeling it off, you're opting for a leaner, healthier option. Additionally, without the skin acting as a barrier, marinades and seasonings can penetrate the meat more effectively, enhancing flavor throughout. Talking about almonds, you must eat them daily so you can remember us and keep watching our videos. Cheese holds a special place on plates globally, with millions indulging in its creamy goodness daily. Hey, if you're enjoying this video, make sure you hit that like button so we'll know how many people are interested in watching our upcoming videos. The ancient Egyptians were one of the first civilizations to enjoy sweets, using honey as a primary sweetener. That minced meat, also known as ground meat, is incredibly versatile and used in a wide array of dishes worldwide. From savory meatballs to juicy burgers, its adaptability knows no bounds. It all boils down to freshness and food safety. Ideally, you want to consume tray-sealed meat within a few days of purchase to ensure peak freshness and flavor. Let's crunch into the world of factory-made delicious potato chips. From sourcing the finest potatoes to adhering to strict quality control standards, these factories ensure that each chip meets the crispy, satisfying standard you expect. These machines are the backbone of large-scale food operations, capable of handling a wide variety of produce with speed and accuracy. These factory-prepared meals undergo stringent quality control measures to ensure they meet safety and nutritional standards. From automated sorting systems that ensure only the highest quality ingredients make it onto the production line to state-of-the-art packaging machines that swiftly seal products for freshness, these machines are essential for meeting consumer demand while maintaining high standards. Each pepper is carefully inspected for size, color, and quality, ensuring only the best make it to market. Each juicy bite is a refreshing explosion of tangy sweet goodness, leaving taste buds dancing with delight. These innovative contraptions are designed to streamline the process of pouring batter with precision and consistency. These machines are the masters of precision, effortlessly dispensing just the right amount of batter, dough, or filling with each press of a button. That's where the multi-head weighing machine shines. Its multiple weigh heads work simultaneously to ensure accuracy and efficiency. Imagine effortlessly removing the outer layer of fruits and vegetables with precision and finesse. That's the magic of these machines. From potatoes to oranges, they strip away the tedious task of manual peeling, saving you time and labor costs. But it's not just about convenience, it's about consistency. With peeling machines, you get uniform results every time, ensuring your products look as good as they taste. Wait, before watching this clip, were you thinking peeling fruit is the hardest thing to do? I mean, it's messy, but not anymore. It's not just about indulgence, there are benefits too. Chocolate breads pack a double punch of flavor and nutrition. Bursting with tropical flavor and juiciness, mangoes are nature's candy that never disappoints. From automated temperature control to efficient oil filtration systems, they're designed to optimize performance and minimize waste. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, The mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel's structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms or high-speed diverters organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data embedded in barcodes or RFID tags about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars' global standardization team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as overconching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances, that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of two primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts equipped with vision systems scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, Texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact.